Hello, welcome to today's segment of our lesson. Today we'll still continue from where we stopped in our last class. We dealt with static forces in our last class, and today I want us to do more justice to statics. But before that, let us look at the previous lesson. Okay, welcome back. Now, when we talk in our last class, we made mention of static. We said static deals with the effect being felt by a body due to its position at rest, of which we used an illustration of a cup. We used illustration of a cup being acted upon by forces. So today I'd like us to do more justice to this. So let's say this is our cup, and forces tends to act on it, on this cup, and there's another force acting in this direction, another force is acting in this direction, and the normal react, and an upward force also acting on this same cup. So the forces and their distance, we said something about it has to do with moment. So today we are saying that force is the action that tends to change the state of a body at rest or uniform motion in a straight line. Now, according to Newton's third law of motion, you could still remember he said action. Okay, first law of motion, when he said a body Newton's first law says a body will continue in its position until an external force is acted on it. Now, the same thing happens here. You say force is an action that tends to change the state of a body at rest. Now, this is a justification of it. So, if a body is at rest, it will continue in that position until if a force is being acted on it, because the main cause of motion is force. So, you talked about force as being the pioneer of a uniform motion in a straight line. The same thing is applicable in static. We are saying that for a body to be at rest, series of forces are acting on that same body. That is what is keeping this body at equilibrium, and the body is not falling off from its position. Now, when you talk about polygon of forces, according to our knowledge in physics, say is a broken line that is constructed to determine the resultant vector. There's a geometric sum of every given system of forces. Now, this is a parallelogram. I want us to create a straight line from this point to this point. Now, when you talk about the polygon of forces, you're talking about some set of dotted lines from here to here, and from this point to this point. Now, these dotted lines are constructed, and they help in, let's call it theta, and let's call the angle here as phi. Now, these dotted lines are so constructed. Okay, let's draw a better polygon. We have this, we have this, and we have this. Now we have dotted lines that projects in this direction. We also have dotted lines that comes in this way. Now, let's say the angle here is theta, and this is a parallelogram. These dotted lines are called polygon of forces because these broken lines are constructed and they help us to determine the resultant vector. That's the geometric sum of a given system of forces. Now, when we move further, I'll give you a detailed explanation on how this can be calculated and how they can be used in determining the geometric sum of a force that acts in a given plane. Now, when we talk about resolution of forces, you know, normally when we have in our geometry, we have the cardinal points. We have the north, the south, this is the east, and this is the west. Now, in geometry, the right part of it, which signifies the east, is called the x-axis, while the upper part of it, which stands as the north, is called the y-axis. This is the negative. Okay, this is also the x-axis, but with a negative x, and this is a negative y. So we are interested in converting forces into the positive and the positive values of y and x respectively. Example: if this happens to be a cup, I know you'll be wondering why I like using cups so much. It's because of my love for tea. So let's say this is a cup. I love coffee. So, for this cup to exist at this point, a force is acting in this direction to hold it. Now, there is also a reaction that is holding the cup. This is called there's another force acting on this cup. There's another force acting in this direction to stabilize this other one. There might as well be a force acting from this direction, and as well there might also be a force acting at this direction. You can see that we can have a total of 1, 2, 3, 4, 5, and 6 forces acting at a given point. But our interest in resolution of forces is for us to compress this force into the positive x axis and the positive y axis. That should just be our area of concentration, resolving them into the positive x axis and the positive y axis. Now, how can we achieve that? We can always do that by applying our normal Pythagorean theorem in trying to justify a simple formula in converting this into the positive. Let's do it this way. This are polygon line that will justify it. Let's call here the resultant P. Let's call here X, and let's call here Y. Let's call here, okay, we can still call it, this is supposed to be our Y, and this is supposed to be our X. So with this, what we have here, we can clearly state, this diagram need to excuse us. Let's produce a better diagram here. These are X axis, these are Y axis. Let's call this point theta. This is a resultant. Then let's call the polygon. This is a polygon line of force, just like what we discussed in our previous class. So with this, we want to get the value of y. Remember our normal arithmetic that is a rule called XOH, CLH, and TOA. This is termed SOHCAHTOA. Now let's concentrate on y. Remember, we're talking about resolving this force, and this is the resultant force. So let's look for which of them that has a relationship between the opposite, which is y, and the resultant, that is opposite and the hypotenuse. Opposite and hypotenuse, which is sine. So we are taking the angle, we are solving. Sine theta is equal, the opposite is y, all over the hypotenuse is r, which we call p. So in getting y, so therefore our y is equal p sine theta. You've seen that the value of y, that this is the vertical axis. If we want to resolve this force into the vertical axis, we resolve it using the sine. Now let's look for a relationship. Let's resolve the horizontal axis. Let's look for a formula that connects x and p. So that is adjacent and hypotenuse, which is cos. So we now have it as cos theta is equals a is the adjacent, x all over hypotenuse happens to be the p. So in getting this, we have our x to be equals p cos theta. So when it comes to force resolution, this is the this one is for the horizontal, and this is the vertical. So whenever we are resolving forces, in resolving forces into the horizontal component, we make use of P, the resultant and the cosine of the angle. While if you're resolving the vertical component, you make use of the resultant and the sine of the angle being given to us. I would like us to apply this in the question we have on the screen. The question we are seeing here that will enable us to go into detailed understanding of what we have. Now, from our question, the question here says a force P of 230 Newton. Okay, let's just draw the force in this direction, in this manner. 230 Newton. This is a force. There's no direction yet. Let's know where it's moving towards. It's inclined to a horizontal at an angle of 25 degrees. So the angle of inclination is 25 degrees. So let's produce it. They said the angle of inclination is 25 degrees to the horizontal. So let's continue. Our angle of inclination is 25 degrees. 25 degrees. Find the horizontal and vertical component of P. Now this happens to be the vertical component, and in a vertical component, let's call it Y. The horizontal component, let's call it X. Now I told us something that if we want to get the vertical component, we make use of sine. So the vertical component, which is Y, is equals P sine theta, where our P is what? 230 Newton. So we have 230 sine 25. So and the value of sine 25 is, okay, we now have 230 times sine 25 is 0.4226, which is equals 97.2 Newton. So this is our this one is the vertical component. Now let's deal with the horizontal component. If you want to talk about the horizontal component, that let's say X, I told you that it is P cos theta. So with this, our P is 230 times the cosine of 25, and we now have 230 times cos 25 is 0.9863, which is equals 208.5 Newton. So this for the horizontal component, 208.5 Newton. Now, one of the things I want us to take into consideration is that whenever you want to check the value of cos and sine, make sure that the calculator you're making use of is usually in degree. At least with that, because we have radians, we have degree. Make sure your calculator is in degree so that you get the actual value of cos 25 and that of sine 25. I think with this is a very fast, refreshing point, just like what we had before today. And I think we've done justice to this. So I would like you to take this test that will be coming up in your screen, and do well to use the lesson notes on this platform for a better information on the topic we've discussed. Feel free to drop your questions on the comment section, and hopefully it will be attended to as quick as possible.